All right, so we left off, we talked about the SN2 mechanism. We talked about the approach of the nucleophile and how it comes in opposite to the leaving group. We talked about the transition state, which is shown here. And that's also going to lead us into another discussion about the rate law, as well as the factors that affect the rate. I think I sent you some information on Monday dealing with the ICE method, how to identify, characterize, and execute these reactions and know which mechanism is taking place. And then I think I also sent you a video about the solvent and why protic and aprotic solvents have different effects depending on the mechanism. And then I think I sent one more video dealing with it was either the rate or some other aspect of this reaction. Anyway, so you can see right here, we're going to open up here that in the transition state. Wow, it's the fifth already. In the transition state of this reaction, you can see that both the nucleophile, which is right here, and the substrate are involved in the rate determining step. Right, so nucleophile and the substrate are involved in the rate determining step. So what that means is that when we calculate the rate, we have to include both of those terms in the rate. So for SN2 mechanism, right, the rate law is going to be K times the concentration of the substrate and the nucleophile. So it's a two-term rate law. The reaction is second order. Overall, how do we determine the order of a reaction using the rate law? What numbers would we use for that? If this is all you had, how would you determine if it was first order, second order, third order? How would you know that? So in the rate law, the exponents here are 1. So if you add those together, since the rate is a product, you would add those exponents together and you get 2, right? 1 and 1 is 2, so a second order overall, right? So what that means in terms of reactivity is if I change either the nucleophile concentration or the substrate concentration, is going to have an effect on the rate. So if I doubled the substrate and the nucleophile, the rate would increase 4 times. Right? So whatever I do to either one is going to affect the rate. If I triple them both, then it'll be a 9 times increase. If I cut one in half and double the other one, let me move this down. Right, be no change. So the point is, both the substrate and the nucleophile affect the overall rate. All right, questions about that? And that's because the rate determining step involves both those species. Any questions about the rate law or the rate or the overall reaction or anything? All right, the other part of this I want to talk about is the solvent effect. And I'm going to just box it in here. Really? All right. For those who are awake, we'll talk about the solvent. If you sleep, you can log off. All right. So we said that for this reaction, right, it works best in aprotic solvents. What does that term aprotic mean again? Anybody who's awake?
Aprotic means that it doesn't have, well, does it say that it loses a proton, or
It can't lose a proton. So it doesn't have any to give away.
Okay, right.
Right. And there's a reason for that, right? So if you do this in a aprotic solvent, and let's say your nucleophile is one from the example. If you do it in a aprotic solvent, the protons are just going to surround your nucleophile and lower its energy. This is called solvation. So the protons trap the nucleophile and lower its energy. And if it's lower energy, it's going to be less reactive. Right. So that process of solvation is that's why you don't use a aprotic solvent for a reaction that you know is SN2. Because once the nucleophile gets solvated, it gets lazy, and that's going to decrease the rate of the reaction. So the way you think about this in terms of an energy diagram, right? So here you have, let's just say without, so this would be an aprotic solvent, right? And this is my nucleophile, right? In a aprotic solvent, that's going to be different. That nucleophile energy is going to be here, and it's going to take longer to get to that transition state. Right, so that nucleophile is lower in energy. And that means you're going to increase activation energy. Because you can see right away, if we are, let me move this. If the black curve is representative of doing the reaction in aprotic solvent, and then the purple curve is protic, the activation energy here is less. If you remember that from part 1, right? And from CHEM part 2. Activation energy here is the energy to get from the start material to the transition state. If you look at that same energy, I'll redraw that, for the purple curve is higher. So that means that the rate is going to slow down. So it's the same. That's a huge difference, right? Because it's the activation energy that controls the rate. So for, if you do this in a product solvent, it's going to slow the reaction down. All right, questions about that? So anytime your nucleophile gets solvated, then the reaction rate decreases, and that's not good, right? You, if anything, you want to increase the rate of your given reaction, not decrease it. Right, the rate will, anytime you increase activation energy, you decrease the rate. All right, any questions about that? So in a product solvent, right, that has H plus to donate, it's going to slow that reaction down. So let's, if you have the handout on this page in the handout, there are some different solvents listed. It's also listed in the video that I sent out. But these are examples of polar A product solvents, right? Acetone, ethyl acetate, acetonitrile. Sometimes you'll see this written as ethyl acetate. This will be written as CH3CN, right? DMF, DCM, THF, all of these are A product. They cannot donate H plus, right? And if you're looking at the amide, well, the formamide proton or formamide hydrogen is not acidic, right? This is not acidic. Right? If you look here, and under product solvents, it gives you a list of product solvents. All this is in this handout. So acetic acid, any type of acid, it's going to be a product solvent. Alcohols, all product. Water is a product solvent. Carboxylic acids are product solvents. Non-carboxylic acids like sulfuric acid, phosphoric acid, HX, HF, HCl, HBr, anything like that is going to be able to donate a proton. You do not want to do that, do an SN2 reaction in a product solvent. So I have it written here. Product solvents favor SN1, and then A product solvents favor SN2. It's really one of the ways to define which mechanism is going to take place, right? If you go back to the example we did to start here, right? We had a secondary alcohol, and a secondary substrate can go, it can go SN2 or SN1. So the difference in this case would have been the fact that we did this in HCl, right? Which would amount to being a product solvent, right? So that's one of the ways to distinguish between SN2 and SN1 is by looking at what solvent the reaction is happening in. All right, let's look at this second example. Somebody tell me what the product is and tell me what the rate law is for that example.
The product is going to be, does the DCM matter?
No, good question. So normally the solvent does not participate. right? Normally your solvent doesn't react. So it matters in the sense that it's a product, but it doesn't matter in the sense that it's not a reactant.
Okay, so because there's no, shouldn't there just be another carbon bond formed and then a loose iodine?
In the
Because
product,
because
yeah,
there's nothing.
no counter ion.
Yeah,
So this is saying it's that plus I minus.
right. And that CH3 is that another bond?
Yeah,
Like, okay,
yeah, because remember, this is my substrate. It's my nucleophile. And then this is the bond that I'm targeting in the substrate. So that CH3 is coming here to attack like that. Right, because iodine is my leaving group. So I'm forcing out the leaving group with the nucleophile and they just swap places. So that CH3 ends up there. So yes. All right. Now, if we look at the next example, it's dealing with the SN1 substitution. So we're going to go through that the same way we did the SN2. And there is a kind of a paradigm map of both mechanisms, but I'm going to use that to review both. Let's add another page. We'll talk about the SN1. All right, we're gonna go back up here first though. So with SN1, this is a totally different pathway. And we talked about it when we did the alcohol to alkyl halide synthesis. We talked about SN1 and SN2. And we said that one of the things that distinguished SN1 and SN2 was the structure of the substrate. So this works on secondary and tertiary carbons. It works better in protic solvents. So we'll talk about why. And it's stepwise, not concerted, like the SN2 is concerted. And you always go through a carbocation intermediate, right? So anytime you do this reaction, there's a carbocation intermediate. So let's look at the first example. A solvent, if you notice, is methanol. All alcohols are protic. So this is a protic solvent, right? This is my nucleophile, my leaving group, and then the leaving group is in this substrate. What's the outcome without knowing the mechanism? What's the outcome of any substitution?
I mean,
Product.
switch the ions.
So we would replace or substitute the leaving group with the nucleophile. Is that right? I mean, I know what you're saying, but I'm trying to give it more nuance because that's what's really happening, right? The only ion in this case is the methoxy group. The bromine is neutral. So we have to say it a different way, but I know exactly what you meant. We're going to take the nucleophile and use it to replace the bromine. All right, so the product of this substitution is that plus that. All right, so let's take that same reaction. I'm going to talk about how it works. All right, so with this particular mechanism, it's not concerted, it's stepwise. And so the first step is loss of leaving group. All right, spontaneous. So the bromine is going to leave. So you can imagine the better the leaving group, the faster the reaction is going to be. So that loss of leaving group will leave me with a carbocation intermediate. Can somebody tell me why tertiary substrates are favored with this mechanism based on what we just saw?
Tertiary may be favored because they're the least substituted, or are they the most substituted?
Think about what we did. We're making a carbocation. What's the trend for carbocation stability? Which carbocation is the most stable?
Oh, yeah, the tertiary.
Tertiary. So for a reaction that goes through a carbocation, wouldn't it prefer to go through or prefer to occur on a substrate that when you make the carbocation that's more stabilized, right? So it's a tertiary substrate. When the leaving group leaves, it becomes a tertiary carbocation. So that's why this is preferred for SN1. And then the next step is the nucleophilic attack, right? Where this is going to come in and attack here. Right, so that's some things that we can talk about here. The first is that the loss of leaving group is the rate determining step. Right, so the transition state for the rate determining step it just looks like this. Where this is a partially broken bond between carbon and bromine. How is that different from the SN2? How's that different? What are the SN2 transition state? We just looked at this. What did the SN2 transition state look like?
In the SN2, don't they all attach and then it forces off the ion versus SN1 where it creates a carbocation?
So the SN2 is concerted, right? Let's go back up to here. Remember, we showed that. So both the nucleophile and the substrate are involved in that transition state, right? Because it's all happening at once. Here, and the reason I'm asking that is because it matters when we talk about the rate law, right? So there's no nucleophile involved in the rate determining step. All right, so when we write the rate law for the SN1, it's just dependent on the substrate, not the substrate and the nucleophile. Right, so it's first order in substrate, the nucleophile is not involved. So with that being said, what if I triple the concentration of the nucleophile in the reaction? What do you think would happen to the rate?
Nothing.
Nothing. Exactly, because the nucleophile does not affect the rate. if I triple the concentration of the substrate, then we should see a 3 times increase in the rate. But if I triple the concentration of the nucleophile, I do anything to the nucleophile, it doesn't change the rate at all, right? It doesn't change the rate. So tertiary substrates work best. Also, allylic substrates work well because they can be stabilized. Any substrate where the carbocation can be stabilized either by resonance or by induction, then it's going to be favorable to do SN1. Let's talk about the solvent. All right. And then I also want to talk about one other thing. Well, actually, before I talk about the solvent, let me talk about this. So with that being said, so we know what the rate law is. A tertiary substrate like that would never do SN2, right? If that was the case, what's the approach of your nucleophile in an SN2? Like, what would that look like? So here's my substrate. Here's my leaving group. Where would the nucleophile come from if this went through SN2? Would it come from the front or would it come from the backside? It would have to come from here, because the nucleophile is not going to come from the same side where your leaving group is. And so when that's the case, this will never happen. What's the term for those carbons that are there on that tertiary carbon, those substituents, the branch points? What do we call that when there's some interference between the substituents and the incoming nucleophile? What kind of interaction is that?
That's steric hindrance.
Steric hindrance. Too much steric hindrance for tertiary. Too much steric hindrance. So this will never go SN2, right? Ever. There's sometimes you'll see SN2 like products with substrates that undergo SN1, but that's in rare cases where you have like the leaving group leaves, but it stays closely associated to the carbocation, but that's really rare, really, really rare. The other part is the solvent. Let's talk about that. And then we're going to work through a couple of these examples. And then we're going to start working through some substitution problems. So product solvents actually are favorable for this mechanism. And really for the same reason that they are disfavored for the SN2. I'll zoom out, so don't worry about that. So product solvents are favorable for SN1, right? The nucleophile is not involved in the rate. So if it's solvated, it doesn't matter. It's not going to slow the rate down. But if you think about a product solvent, and think about this from in terms of the transition state, where you're losing bromine, right? The solvent can actually solvate the leaving group while it's leaving and stabilize it. So this is the same reason solvation that slows down the SN2 actually facilitates the SN1, because the leaving group is stabilized by the solvent. Right, and this is in the transition state. So leaving group stabilized by the solvent, which is good. That's going to lower the energy of the transition state. So it's going to lower the transition state energy. And it's also, if I lower the energy of the transition state, what else is going to get lowered? Right? If I do this here, right, that's my, so this would be A. Go ahead.
Energy, the
Say again.
activation, the
Activation energy.
activation.
Good. So if I do this in an aprotic solvent and then I do it in a protic solvent, right? If I lower the energy here, then I'm also lowering the activation energy. Good. Right, so that's going to be lower. That's going to speed the reaction up. And if I lower the transition state energy and in turn lower the activation energy, then that's going to lead to a rate increase. Anytime I drop the activation energy, the rate is going to be accelerated. Anytime I raise the activation energy, the rate is going to be decreased. All right, so if we look at any questions about that before we move on to something else. So we talked about for SN1, the actual mechanism, how it happens, the transition state, the solvent effects, and the rate law. And if you look on this page of the handout, it has like an overview for both. All right, so we'll look at let's look at the SN2 one first, where we already talked about this. The rate determining step is concerted. Nucleophile coming in, leaving group leaving. That's concerted. All happens at the same time. No intermediate. And the transition state is overall negative because your new incoming nucleophile is negative, your leaving group, well, partially negative, and your leaving group is partially negative. So the overall charge on the transition state is negative. And then we talked about this, the nucleophile comes from the opposite side of your leaving group. And with the rate, you can increase it with good nucleophiles and good leaving groups. There are better nucleophiles than others. Some nucleophiles are better than others, and especially depending on the solvent. And we're going to talk about that. I don't remember. Did I send that video ranking nucleophiles? I think I did, or I may not have, but I will. Right. So let's talk about the SN1. And then we're going to talk about how to tell what's a good leaving group and what's a bad leaving group. So for SN1, this is the overall reaction, right? You lose the leaving group, you make a carbocation, and then that gets attacked by your nucleophile, right? So this works on tertiary, allylic, and benzylic carbons only because the cation is stabilized. So rate determining step is stepwise. The loss of leaving group is the rate determining step. So it's a two-step reaction. You go from start material here to intermediate, and then from intermediate to product, right? And this reaction always proceeds through a carbocation intermediate, unlike the SN2. And we talked about this already. The loss of leaving group is the slowest step. This is the transition state, what it looks like. I just showed you that in a real example. This is just a generic example where you have your substrate, your departing leaving group, and the overall charge is neutral. Because this is partially positive, that's partially negative. So the overall charge of that is neutral. And then here, I think when I sent that ice method video, I talked about one of the ways to identify SN1 is to look at the stereochemistry of the product. Remember for SN2, we talked about this already. You see inversion. For SN1, what you see is mixing or racemization. And that's because with the carbocation that you make, there's no preference for how the nucleophile attacks it. This is in the case of a reaction happening at a chiral center, right? So we'll look at some examples of that. Right, so good leaving groups, stabilized carbocations, increase the rate of SN1. Good leaving groups, good nucleophiles, increase the rate of SN2. Right, and then we talked about the solvent already. SN2, we want to do that in aprotic solvent. SN1, we want to do it in a protic solvent. Then inversion of stereochemistry versus racemization of stereochemistry. All right, so let's look at the leaving groups, and then we're gonna go through and work through some examples. And that's what we'll be doing between today and Friday, is working through some examples so that we'll have on the exam, it'll be up to SN2 and SN1. So we'll just work through the SN2 and SN1 examples, and then Monday we'll start elimination, and that'll be on test 3. So elimination won't be on this exam. So with the leaving group ability, right, this is really based on the pKa of the conjugate base. I'm sorry, pKa of the conjugate acid. Based on the pKa of the conjugate acid. Right, so here is a list of leaving groups. You can see right here, iodine is an excellent leaving group. It's at the top of the list, right? And there's a reason for that, and it's here. If you look at the conjugate acid of iodide, which is HI, it has a pKa of -10. How many of you remember from part 1 when you studied pKa, and we talked about, well, not we, but whoever you talked about, or should have talked about, the pKa of an acid being based on how stable the conjugate base is. And the conjugate base can be stabilized by hybridization, induction, resonance, size, or electronegativity. And y'all remember that, anybody? If you took the class this summer, even though it was online, you should have seen the Hires mnemonic, HIRES. Right, hybridization, induction, resonance, electronegativity, and size. Right, so iodine is obviously a very stable anion, right, or a very stable conjugate base because of its size. Where it is, it has a large atomic radius, and that negative charge you can spread out over a larger surface area. So that's why it's such a good leaving group. Same thing with bromine, chlorine, but if you notice, the ability is decreasing because the conjugate acid pKa's are also getting larger. If you remember that from part 1, higher pKa's mean that the acid is a little weaker than a acid with a lower pKa. But these, if you go through the list, then you'll see, as you go from iodide all the way down to methyl is a horrible leaving group, right? And that's because the pKa of the conjugate acid, which is CH4, is 49. That's a really, really, in terms of being an acid, it's really not an acid, but it's so weak. It's a ultra weak acid. It'll never give up that proton readily. All right, then you have some other decent leaving groups, Fer in here. Acetate is a decent leaving group. Sometimes you'll see this written as OAC. Right, ammonia is a decent leaving group because the pKa of the conjugate acid for ammonia is, which would be NH4 plus the ammonium ion, 9.2, right? So this is just a way to tell what's good and what's bad. And you'll have, on an exam, you'll either have the number, the pKa of both leaving groups. If you're comparing a reaction, you'll have the pKa so you can make a determination. But a lower pKa is a better leaving group. Higher pKa, worse leaving group. All right, questions about that? This is one of the ones you're going to see as well. This is a Tosylate. And it's abbreviated as OTS. All right, any questions about the leaving groups? And again, if you know the pKa of the conjugate acid, you can estimate how good or how bad a leaving group is. Remember when we were doing the alcohol conversions and we said that the OH is a bad leaving group. If you look down here, right, it's in the poor to bad leaving group section. And that's because water, which is the conjugate acid, has a pKa of almost 16. So it's not a good leaving group at all. And it's not, that means that when it leaves, that negative charge that's on oxygen is not stabilized very well, as it would be if oxygen was able to do resonance, or if it has some type of inductive group next to it. And then this is also another good leaving group. It's a triflate. You'll see it written as OTF. All right, let's go to, let's look at these examples right here in the last 2 minutes. Not the top example. Let's go to here. We'll answer number 2 and 3. And then on Friday, we'll open up and answer the top example. So this question asks, what pathway would you expect the following reactions to follow? So if I had these two reactions, the way you approach this is to identify everything. So you look at your substrate, look at your leaving group. So you have your substrate in both cases is secondary. So that can be SN2 or SN1. The tosylate and acetate both are decent leaving groups, right? So that the rate is not going to be impacted very much by either one. This is your nucleophile. It's a good nucleophile. And then your solvent is aprotic. So with a secondary substrate that can be either SN2 or SN1, but you have a solvent that's aprotic, what mechanism do you think is going to prevail here? In an aprotic solvent.
The one aprotic is going to be the whichever one doesn't require an H to I guess maybe the PK, well, the
wouldn't it be SN2? Let's go back up to here. We said that for the protic solvents, we can just go right here. Protic solvents favor the SN1 mechanism. Aprotic solvents favor SN2.
is that where you explain that it would come in from a certain direction?
No, that's different. That's talking about the actual substitution, like the rate determining step. But this is dealing with the fact that if you do the SN2 in a protic solvent, it's going to slow it down. Remember, we talked about that up here. So for SN2 mechanism, if you use a protic solvent, it's going to solvate your nucleophile and slow the reaction down. SN1, if you use a protic solvent, it's going to speed the reaction up because it's going to solvate the leaving group. So here, if you're doing the reaction in a protic solvent, in an aprotic solvent, then that's a clue that it's a SN2 mechanism, right? If it's aprotic, that means it's going to favor SN2. So we're going to say that this is SN2. Now, having answered that question, let's do number 3 and then we'll stop. So based on the answer to that question, what's the right rate law? If we know it's SN2, what is the rate law for a SN2 mechanism or SN2 reaction?
It's going to be whichever one excludes the and nucleophile, which would be,
Does it exclude it or include it?
oh, I got it backwards. It's included.
It should include it,
Okay.
right? It's not B
Okay.
because that's the solvent, and the solvent does not play a role, and it can't be either one of these because neither one of these include both the nucleophile and the substrate. So it's here, right? Because the rate of a SN2.
Okay, so I had it backwards. So S includes the nucleophile, but SN1, the rate isn't affected by the nucleophile.
Right, exactly. Exactly. All right, we're gonna stop here. We'll pick this up on Friday and then the test will be posted like last time, just posted over the weekend. So we'll stop here. Let me stop recording.